All right, in this video what we want to do is do part of the proof of this 17.3 test for conservative vector field. So this is from your book, and here it says let f, which is a vector field, equal fgh. So this is in R3. We're just going to do the proof in R2. So instead of capital F equaling fgh, capital F is just going to equal fg. It's going to be in R2, okay? Defined on a connected and simply connected region D of this is R3, and F, G, and H have continual first partial derivatives on D. So that's going to be the same thing for R, F, and G down here in R2. Okay, so all this criteria has to be met. Then F is a conservative vector field on D, and then we have what the word conservative means. If and only if all three of these equalities are true. This would be in R3. These criteria are for R3. For a vector field in R2, we have the single condition that this partial has to equal this partial. Okay, so we're just going to do this one in R2 here. Okay, and we're going to prove it in one direction. Now, what I mean by that, when you have if and only if in a theorem, it's bidirectional. So that means you could switch the if and the then part. So this theorem is saying, hey, if you know f is conservative, then these partials, whichever you're doing R2 or R3, would have to be equal. Now the converse of that is also true. That's the if and only if part. If you somehow knew that these partials were equal, then you could conclude that f is conservative. And we use that a lot in order to test that f is conservative. We're given some f, and we take this partial and we take this partial. Oh, are they equal? Awesome. Then it's conservative. So we're doing this direction, okay? So we're just going to prove one direction. We're going to prove that if f equal fg is conservative, then these partials are equal. We're not proving the converse here. That proof is in your book, and it's a little more extensive if it's something that you want to look at. Okay, so this is our given information. We know f is conservative, which means that f is equal to the gradient of some phi, for some phi that's a function of x and y. And we're going to show that these two partials are equal to each other. So this is what we're going to start with, and this is where we're going. All right, let's do it. So what we're given is that f is conservative. So since f is conservative, that means we know that f is equal to the gradient of phi for some phi, which is then equal to the partial of phi with respect to x, partial of phi with respect to y. Okay, and since f, capital F, is little f, little g, that means this is little f and this is little g, right? So little f is equal to, and let's write it this way, partial x, oops, I said it right, but I wrote the wrong notation that I wanted, partial phi, partial x, and little g is equal to the partial of phi with respect to y, right? So it's just the same notation. This notation means this notation right here. Okay, so now what we're going to do is we're going to take this first equation right here, and we're going to take the derivative with respect to y on both sides of that, the partial. Let's see, I'm going to write it out down here. So we're going to take the partial with respect to y of both sides of this. And we're going to take the partial with respect to x on the other one. Partial with respect to x on both sides. Partial, I'm trying to make those not look like twos. G equals partial phi partial x. All right, let's think about what we get here when we do that. Multiplying those. Well, we're not multiplying. We're just taking the partial. Okay. So here we have partial f, partial y. That's pretty straightforward. And what we have here is a mixed partial. So I don't know if you remember when we did these, you could, when you have a function of two variables, you can take the partial with respect to x and then the partial with respect to x again, like a second derivative, right? So if you have phi, you can take the partial of phi with respect to x. And then if you do a second derivative, well, you could take it with respect to x again, or you could take it with respect to y. And so we had 4 of the second partial derivatives. Do you remember this? Yx. When we do a second derivative, we've got 4. And then we showed for nice functions that these mixed partial derivatives, meaning one is with respect to x and one is with respect to y, that the order didn't matter for nice ones. All right, so what we have up here is the second derivative of phi first with respect to y, or first with respect to x, then with respect to y. And then over here, we have partial g, partial x, is the second derivative of phi, second partial. Oh, sorry, I copied this wrong right here. You probably caught it right there. This is supposed to be partial y. I wonder if I said it wrong too. Okay, partial phi, partial y is g right here. I knew that was coming out weird because I know these are supposed to come out to be mixed partial derivatives where the order is switched. So see here we have these mixed partial derivatives, second derivatives, but the order is switched. So by this theorem we talked about, if we have a nice function, now how do we know we have a nice function? Well, let's go up here. We have a nice function. All right, we have continuous first partial derivatives on d. Everything's nice. So I know that these two things are equal to each other, these mixed partials. So since the mixed partial second derivatives are equal, we know then that partial f partial y has to equal partial g partial x. Okay, so we know this blue business is equal to this blue business here. So since those two things are equal to each other, then they're both equal to these guys. So these two things would have to be equal to each other there. And that's pretty much the proof. All right, we started off with the fact that f was conservative and basically just set these two little single partial derivatives equal to f and g and took the partial with respect to y of f and x with g, and then used the mixed partial derivatives being equal, and there you have it.